Okay, let's get started. So last week we talked about how to return to a piece of shellcode, and that piece of shellcode will just give you a shell, and you can see I did that on my computer, and the shell returns you have the effective user root. So today we want to do that on the server, which is a little bit harder than I do that on my local computer. And also for your homework, everything, you are going to do that on the server. So there are two major reasons why doing that the same thing on the server is a little bit harder. First is on the server, we're not going to use that tool r.sh to balance the stack. So you do not really know the exact address of the return, which means like we did last week, we're going to have some big sled there. The sled is just a very long loop instructions chain. Of course, the loop instruction doesn't have to use the loop instruction itself, right? The loop is 98 in hex. You can use that where after the CPU to not do anything. You can use other equivalent instructions, which equivalent to doing nothing as a loop, obviously. So that is one small challenge. The another challenge is actually the server we're using. When a set UID program, the process is replaced, we replace it with a shell program, right? When it is replaced, the privilege of that one is dropped. It doesn't really inherit the root privilege of the original set UID program, which means we're not going to use the same shellcode we used before. Okay, so there are several challenges there. I will show you step by step. So, and we're going to debug about things so you can. So the purpose of this is for you, every time you see a problem, don't panic. Think about what is the root cause of problem and how I can solve that. Okay. So there will be several demos today. After that, if we still have time, there is another challenge which is not on our server. It's on another public server opening available. Then you can try to solve that one. If we don't have time, then that will be your homework. Okay. Before we talk about how to do that on the server, let me remind you what the vulnerable program look like. Very simple vulnerable program. Main function calls the vulnerable function vulfu, then you print out IP the full. So in that vulnerable function, we have a buffer at a shellcode level, 30 bytes. I emphasize this many times. That doesn't really mean at the instruction level it's 30 bytes. You have to look at the disassembly, the machine code to see how many bytes are there. Then there is a get function to get input from std in. Get is a little bit different from string copy. String copy will stop copying things when it says a 0. Get doesn't do that. Get will keep copying until it says a new line or something like that. So it's okay to have zeros in your shellcode when the vulnerable function here is gets. So the vulnerability here is you can obviously input some super long things to overwrite the buffer and overwrite everything above the buffer, including the return address, everything. This is a 32-bit code. What the disassembly and the stack look like. Last week, I showed you your first shellcode, which gives you a shell. The shell we're using is bin/sh on the server. Bin/sh actually points to dash. So there are many ways we can craft the exploit. First, from the disassembly, we know how big this size is. It's actually 48 bytes. So we can put the shellcode, which is 28 bytes, and in front of the buffer, then point the return address to the front of the buffer. Okay. In this approach, it means you have to know exactly where the beginning of buffer is. If you are 1 byte off, you're not going to execute the full shellcode. If you are 1 byte pointer 1 byte lower, you're going to execute some garbage here. You don't know what that is. That may trigger a segment fault. If you are 1 byte higher than this, you are jumping into the middle of an instruction. You don't know what will happen. Okay. Another way is you can put 20 bytes of knobs in front. So this gives you 20 bytes of cushion here. As long as the return address jump to any of the 20 bytes, eventually the control will be transferred to your shellcode. That should work. But in this case, your knob is not that big. The sled is only 20 bytes. To increase your chances, obviously you want to make the knob sled even bigger. So what you can do is you can you do not put anything in the buffer. You put the return address here. Then you put a huge loop after the return address. After that, you put the shellcode. So the return address here you need to point to is anywhere in the loop. In this case, your loop can be much bigger. In the commands I'm using here, the loop is actually not that big. This is 30. This is 30. Sometimes you can make it huge. You can make it thousands of bytes. Depends on the system you're using. So we're going to do this on the server using the same approach, and you can see there will be a lot of challenges. First of all, the challenge is we're going to use a program. We are going to use the program 32-bit first. Overflow return 4 32-bit. First, we want to at least have a rough idea where the buffer is, right? Well, we can guess blindly because we know the stack is always on the top anyway, so it will be FF something. But to get a rough idea, we can use a GDB to do it. So with GDB, we set up a breakpoint at the val-foo. Then we just run this without giving any input. Then we do disassemble here. You can see this is a val-foo function, and this is a gets, and this is a push. So add here EAX, or after this one, we know EBP minus 30 in hex. That's where our buffer is, or in EAX. We kind of want to find out where it is roughly. So we keep going on here, maybe FA or FD. Then we can do a print. We want to play hex, print a hex. That's why we do that. Then in GDB, if you want to print the value of a register, you do $sign EBP, right? EBP minus 30. It can do the calculation for you, or you can do a EAX. That will be the same thing anyway, right? Okay, so you can see without, when we run this program in GDB, this is where our buffer is. But without the GDB, the buffer will be at a different size. When you use GDB, GDB will always push something onto the stack. So this address will be lower than without GDB. And also in GDB, if you get it running, GDB cannot get a set. We cannot really debug a set UID program. When we debug with a GDB, the set UID program doesn't have the root privilege. Okay. So this is the address we want to copy somewhere here. Okay. So now we want to craft our exploit. Let's use something we have here. Let me say, this one will work, right? Yeah, let's just use this one. Oh, by the way, when you copy from my slides, you need to make sure you are not copying any weird characters. For example, there's a new line here. And also sometimes it could be Unicode, so you need to fix that when you copy from my slides. Let's try if it works. Let's say, oops. How do I fix that? Oops. Let me get a Gmail. I'm trying to fix this. Okay, this should work. Okay, it successfully returned us the string. Let's see what we have. We have 48 bytes of garbage, then another 4, actually 58 bytes of garbage, then the address. Okay, the address is not what we want, right? What we have there is D648. We know it would be higher, so let's just do D700. Then we have we can have now we can have a huge stack, right? Let's try the 3000 bytes of stack. Let's see if it works. Then after that we have the shellcode. Okay, looks good. Then we pipe this into our tolerable program. Let's see what happens. Does it work? Nope, we got a segment fault. So now you get a segment fault, and this is sometimes you don't know what to do. Okay. Like I said, every time you don't know what to do, you should debug. Figure out why you are getting a segment fault. Okay. Of course, you can try more times. Maybe the address is even higher than this. So we try D9. Let's see if it works. Nope, still doesn't work. Let's try E0. Nope, doesn't work. Okay, so in this case, we debug the program. How do we debug this? First we can put this into a temp file. Let's say there is a temp file for the exploit. This is a temp file. We put the exploit into the temp file. Then we debug the program. We debug the program again. Now we set the vol full here. Then when we debug this, we want to run this program, but we want to run with our exploit. So this is the syntax. We do R, which means run, then the redirection, then we put our exploit here, temp exp. So now we are in vol full. Let's take a look why we get a segment fault. So we keep running. Where we are at here right now, we're still not doing gets. FD, we're here, we're all together gets. Okay. So what's the problem is? When you debug this, you realize the problem is when you're doing that memory copy, when you're doing gets, and the system eventually do the memory copy, there is a segment fault. Okay. It's not because you overwrite anything yet. You haven't overwrite. It's because you are calling that library function, you are getting segment faults. Okay, so the reason for this is probably the system doesn't support you have a long input like this. You haven't copied everything there yet, then there is segment fault. That's probably because our set is too big. The program cannot handle that. Okay, so then we use a smaller set, 500 bytes. Then let's try it again with a 500 byte sled. And we start at a lower address, D8 or something? Oh, it was D6, so it will be higher. Then let's try D8. Oops, I should not do this. Type this into the program. Okay. Oh, we got lucky. The first time we do it, we got it. Okay. Looks like we got the shell, all right? The shell is running. However, you will see another problem. If I do who am I, you can say who am I? I'm CPF. I'm not root. That's because in our server, the Ubuntu we're using, when we create a new program, no matter the program is a shell or what, the new program doesn't inherit the old program's root privilege, which means we have to get the flag in the old program instead of create a new shell. So how do we do that? Any idea? How can we do that? We're not going to get an interactive shell. But why do we need an interactive shell anyway? Here, we have an interactive shell. If we can't flag, we don't have the permission, okay? So we have to do this in the old program's address space without replacing the old program into the shell. Any idea? Let's get it. It's all about the program we inject there, the shell code we inject there. So far, the program, the shell code we inject there does one job. It gave us a new program, which is a shell, right? To do that, it executes the system call execve. What if we do not execute this system call? Instead, we do other system calls. We read the file and we output the file. We do not create a new program, right? So that is what we're going to do. We're going to use another piece of shellcode, and that piece of shellcode is not going to return us a real shell. Instead, it directly will open a file called flag, and that's the flag's location. And so usually when you do C programming, when you open a file, read a file, what do you do? You first use open, then you use read. But you need to output that, right? So you need to read that into some kind of buffer. Then you use a write function or system call to write it. Okay, that way works. But there is a simpler way is we do not use that will make three system calls. When you write the assembly, usually you don't want to write a complicated assembly, especially you need also need a buffer to do so. That's why there is actually another system call, also C library function called send file. In send file, you don't need to read write. You only need to get the system call, not the file descriptor. Okay, so this is what we are going to do. We'll first use open to open that file, and the permission we are going to request is only read only. That's why we give it 0. So after this open, the return value will be what? Will be the file descriptor number for that open file. So we're going to send the content of that open file to another file. And then the other file is stdout, which has a file descriptor 0. Okay. So in Linux, by default, stdin has a file descriptor 0, stdout has 1, stderr has 2. So when you do this open, it's very likely you're going to get the std number. You are getting to get the file descriptor number 3 or 4. Okay. But in one step, we're doing this. We don't need to consider any buffer. We don't need to think about buffer. And this is the offset where we want to send the content of the file. We want to send that at the beginning, so we set 0. Then how many bytes we want to send? Let's send 1,000. We don't really need 1,000, but we do that anyway. All right. So this is the C code look like. So how do we write this in disassembly, in assembly? And this is what we do. This is what the assembly looks like. Okay. In today's class, we're not going to write this, but there will be a shellcode class in which you are going to write those kind of things for different purposes. Today, we just want to understand this. The first thing we do is push 67, then push the other value, and it's actually here, we're just to put the string, the file name flag onto the stack. And there is also a 0 implied at the beginning. That's why that's a string. After that, we move 5 to EAX. Then what is 5? Let's say, I forgot to put a slide there. Let's say, oops, x86 system call table. Here. What is 5? 5 is a system call number. 5 is a system call number of open. Okay, you don't have to remember those things. You just need to learn how to use Google. Okay, so now we are putting the system number 5 into EAX. Then where is ESP right now? We just pushed, right? So the ESP actually points to our string, which is a file name /flag. Well, by the way, in this case, we don't really need the slash. Because let me get out of this here. Because this is the root. This is the root directory, and also this is where the program is. So if without that slash, this is a relative address. So the program will look for the current folder, which has flag. With that slash means this is absolute directory path, which is root. So in this case, they are the same thing. So ESP moved to EBP. So now EBP has the file name we want to open. If you check the open, you can say EAX, you have to put it as a 5. Or EAX, you have to put 5. EBX is where the string is. ECX is flag. EDX is mode. So those two probably just set to 0 will be okay. Then so that's why we are setting them to 0. Then we make system call int 80. So after this, the return value, which is a file opened file descriptor, will be in EAX. Remember that. That's why we move EAX to ECX, because the next system call we are going to make has the system call number of BB. Okay, if you go to this table, you're trying to find where is BB. Here, you can see BB is a system call send file. And a send file, EAX is BB, this one is EBX, right? EBX is output file descriptor. In our case, we're sending it to the terminal, so it should be 1. And this one this is the input, and the input should be the file. So we're moving EAX. That's where we're moving EAX to ECX. Then we're putting 1 into EBX. Then the offset, we just put EDX here, and the number we want to send here, or actually in the shellcode I put 100 hex, which is 256. Here I put 1000, so they're not really consistent. But we know that the file is small. We don't have so many contents here anyway, so this one doesn't really matter. Okay, so this is our new shellcode. So after this shellcode, if this one is not successful, we want to exit gracefully. That's why we have another exit system call here. If you are confident it works, this part is not necessary. So from this shellcode, we compile it. We will talk about how to compile it, how to extract it in the shellcode module. So now I just gave you everything here. So this is the shellcode we generated from this. Note that there are some zeros in the shellcode. Okay, which doesn't really matter because the variable functions gets. Then this is our new shellcode we are going to use. We're not going to use the one which return us a shell. Instead, we have this one to directly give us a shell, give the content of the file. So let's try. What did I click? It should still be there. Okay. So let's do That's why if you copy from my slides, you probably want to fix those new lines. Okay, there's another new line. Okay, so this is our, so this one we don't really need a cat, okay, because we're not going to create a new shell. We're directly executing this piece of code. So let's see what we need to fix here. We need to fix this address. Let's just do some, we know this one is ff, d something, right? Let's do d9, 0, 0. We make the sled a little bit bigger, maybe 600 bytes. Then we just try this, okay? We don't know exactly where the return address is. We just try, okay? That'll work. Maybe the sled is too big. Let's make this part a little bit smaller. 500, I know it works. D9, so previously was D6. Okay, maybe that's too high. This D7. Still not working. Okay. 50. Hold on. Should this be? Should this be 56? It was 52, right? Not 56. I think we were doing 52. 48 plus should be 64-bit version should be 52. Yeah. Yep, it should be 52. So when you do this, you get a flag. So I made a mistake on my slides. So you need to be careful. So 32 bits. This one is not 56. Okay. So we get the flag. So you can copy the flag and which challenge is this? This one, 32 bits. Paste it. You can get the points. Okay. So in all the homework, the points are 0, but for the exams, they will not be. This is all. I can count how many points you can get. Okay. Any questions so far? That's the 32-bit version. Yeah. No, because if it's not a SetUID program, it doesn't have the privilege to read the flag file. It has to be a SetUID program. Other questions? Okay, let's keep moving forward. The next we want to do is we want to hack the 64-bit version of the same program. The challenge we face here is the share code we had just now is 32 bits. That's it. We just need to change it to 64-bit share code. And for 64-bit, things are writing the share code is actually easier. You have seen examples before. The same piece of code, when you compile it into 64-bit version, the code is even smaller, shorter, right? And those are the registers we're going to use when we make system calls or function calls in 64-bit version. So the 64-bit version, when we disassemble that, you can say the function is also a little bit different. The buffer's address is not really changed. The buffer's address is RBP minus 30. Previously, it's EBP minus 30, so it's the same. So the buffer's beginning to the saved EBP is 48 bytes. Both programs have the same. Not necessarily. If you program other programs, sometimes they're not the same. Okay. So here we have the same. 48 bytes. And this is the share code to get the bin sh. Like I said, don't work. But I would just want to show you bin sh could be much shorter. This is only several instructions you need. And you do not do int 80 anymore. You use the direct system call instruction to do that. And also you can use RIP addressing. That's why you can define a string here, then you can reference RIP plus a string, and you can compile the address. 32-bit version, you cannot do this. 32-bit version, you cannot directly access the IP, okay? There's no syntax to do that. So if you get this piece of code, what you need to do is, this is assembly code. You want to get those bytes, the exploits. So you need to compile it, and those are the commands you can use to compile that. You use the GCC. You do not need any C library, so you get the no std library, everything static. Then you compile that assembly code. This is assembly code, and this is the output. So when you compile something, the output is ELF. Like I said in the first week, ELF has so many sections, has so many metadata you don't need. What you really need is just the instructions, the bytes. That's why you can use another tool that's in the standard tool chain, object copy. In object copy, you just dump the text section into this file. Then from the ELF file, then you get all the instructions, all the bytes you need. Okay. Anyway, that's something we're going to do in the share coding module. Today, I'm just going to give you the share code. So this is what the share code look like in 64-bit. We have the same open and the send. However, you can see the share code here is we first move this string. You can see this is the same string /flag. We move it to a register, then we push that register to stack. So we have that string on stack, and we know the address, which is RSP, sorry. Then we move 2 to RAX. Here is a very strange thing. The 64-bit version of the Linux system call, the system call numbers are not consistent with 32-bit. They're not the same system call, do not have the same number. I don't know why they do design this, but that is how it is. So read is 0, write is 1. Then let's say, so the website I open here has both 32-bit and the 64-bit. Then let's find where the 64-bit is. This is 64-bit. Yeah, this is what we want. No, let's just search send file. Send the file. Okay, we find the send file, but let's see. This one is 64-bit. Okay, send file in 64-bit. Send file system call number is 40 or 28. Previously 32-bit was bit. Okay, so that's why the first system call we're going to make, we are going to do a read, right? So that's why we move. We're going to do an open. We move 2 to RAX. And this is the address. RSI is 0. So where should we put this number? Oh, this number is RAX. So the system call number is actually 2 here. Okay, open is 2. So that's why we are moving 2 to RAX. Then we make the system call. We open the file. The file descriptor will be RAX. That's why we move RX to RSI. We make the second system call, which is send file. That's why we have 40 here. Okay. So after that, we have the exit. Then this is the compiled share code. So obviously we can do the same thing for the 64-bit 64-bit version. Okay, 64-bit version, run this. The first thing, here, 56 is correct. Because 48 plus 8, right? 56. Then we have 8 bytes of address. So we need 8 bytes here. Then we have some sled. Let's do 500 bytes of sled. Then we actually need the address on stack. So I'm not sure what that is. So we can debug a little bit. GDB. We just print anywhere. We don't need a very accurate address anyway. Then we just print where RSP is. So see, this is where our stack. This is a valid stack address. So let's just try that. Because we have a huge sled, we probably just need to try several times. Let's try this address, 60, E5, FF. How many F are there? Another FF, then 7F, then we have 0, 0 here. Okay, let's just try. Whoop, we got lucky. The first time we tried, got it. Okay, so we got lucky here. That's our flag. Okay, that's how you can get the flag and hack 32 and 64-bit. Okay, I asked you guys to bring your computer here today. So next we are going to play a game on this website. This website is a little bit old, so I'm not sure if they can handle so many people. If you cannot log in here, you can also try our version of behemoth 1. We copied the binary here, but if you, but for this program, if you run it on our server, you have to use the share code that directly print out to use a flag. If you run on this server, you can use the share code to actually give a share, or you can catch where the flag is. Okay, so you can use both. So use your computer. You can open a terminal, log in this server. They will ask for a password for you to log in, and this is a password. Then you go to this folder, behemoth, and that's where the binaries are. And you are going to hack the binary of behemoth 1. After you hack that, you are supposed to get a shell which the user level is behemoth level 2. So you will be able to catch its password. Okay. So all my slides, including today's slides, I already put online, so you can get the share code for my slides. And let's see how many of you will be able to get this before the class ends today. So Wednesday, we will talk about the other approaches, other places we can place the share code. Okay, how is everyone online doing? Let me stop my recording because I'm still recording there.